Hello, everyone. Welcome to the July program meeting for the SDAA. There's so many faces, lots of new ones, lots of old ones. Yeah, thanks everyone for coming. I think we're gonna, well, first of all, sorry for the slightly cramped situation. Krista did an amazing job finding us this space. We're learning, and hopefully the next one will be a lot more comfortable. We've already had like 3 discussions about it just in the 10 minutes since we realized, oh no, there might not be enough seats. So thanks everyone, and thank you for your patience. I promise the next one, we have 2 months, right, till the next one happens, and it'll be way more comfortable, or we're limiting who can come. I don't know which one will happen. Yeah. Yeah, exactly. If we book a bigger space, make sure you show up for the next one so that we have a reason to justify to the board why we spent so much money. All right, I think we're going to kick off with Dennis. Where is Dennis?
I'm the outreach director. My name is...
Now you have a microphone. You're good. You're good.
Dennis, yeah. That's right. And everybody says outreach is really important. And usually they say, you're going to do something at the banquet, make it quick. So I make it too quick, and then nobody knows what's going on. So when was it?
Last Friday.
Was it last Friday?
Last Friday.
Yeah, at Sycamore Canyon East. And Joel Anderson's henchman came out and gave us a whole bunch of awards, but most of the people weren't there. So,
that's okay.
So, Ken, can you come up and hold this microphone for me? Ken is very useful. We use him all the time. Usually we throw him away, but he's going to be a tripod. There you go.
Here's the certificate.
Yeah.
Here is the proclamation.
There's the proclamation. And if you, Ken will put it in the Tierra del Sol house, or we call it West, right? TDS West, hopefully.
I'm hoping they hand it over to somebody tonight.
So we have all these cool awards. If you take it downtown to Joe Biff's Bar and Grill, they'll give you a free beer. Just tell them I sent you. So there's a lady named Addison Jameson. Please come forward, Addie. Are you there? Addie, come forward.
There you go.
Here's Addie's certificate. I'm going to read the first one. And I won't read the rest of them, but it says, Supervisor Joel Anderson, Certificate of Recognition presented to Addison Jameson, San Diego Astronomy Association 2026, National Parks and Recreation Month. In special recognition and sincere appreciation of your active involvement in recreational activities utilizing our district's public facilities throughout the year to strengthen belonging, play, connection, nature, and well-being through parks and recreations for the betterment of our community, signed by Supervisor Joel Anderson, 2nd District, and the date is July 2026. So there you go, Addison. Very good. Zaire, you're here. Come on up. Hurry up. Come on, old guy. Get up here. Here's your certificate. Congratulations for our outreach.
I didn't bring my glasses. So would you read the last paragraph?
Sure. The last paragraph says as follows. Astronomy Associate, San Diego Astronomy, what?
There, right there.
Yeah. Be it proclaimed that I, Joel Anderson, by virtue of the authority vested in me as 2nd District Supervisor for the County of San Diego, do hereby proclaim this 24th day of July 2026 as San Diego Astronomy Association Day in the 2nd District to recognize the San Diego Astronomy Association's outstanding commitment to science education, community engagement, and inspiring generations of residents to discover the beauty, wonder, and limitless possibilities of the night sky. So it was funny because they gave this to us at sunset, so we could only celebrate it for 4 hours. So thanks everybody who's involved with outreach. If you can stand up and show everybody who you are. Prince William, Stan, there's so many of you that... That's why we're tax-free. We're a nonprofit, so it's really important to keep outreach going on in our club. If you haven't done this yet, gosh, just mark your calendar and come on out. You don't need a telescope. So thank you very much.
Thank you, Dennis. Let's hear it for Dennis.
Dennis.
But let's hear it for Dr. Jared Roberts. And yeah.
Professional, man. Hey, everybody. Yeah, my name is Jared Roberts. Do you mind actually turning that down just a little bit? I tend to project a little bit. Yeah, I work at UC San Diego. I'm a associate project scientist as of this year at UC San Diego. That means most of my time I'm actually doing research. We do have graduate students in our class or in our laboratory, and we do mentor graduate students and undergrads and postdocs. But most of my time is spent in the lab working on instruments, mostly space instruments. So although I'm talking mostly about gamma ray astrophysics science today, most of what I do is more in the instrumentation side of things. So it is, I'm familiar with the subject, of course. It's like the area of expertise that I fell into, but I'd say more specifically, I work in astrophysics instrumentation. Okay, and I'm hoping that this talk will be interesting to all of you. I just recently came into astrophotography as a hobby, which it's been an obsession ever since I took my very first photo of stars. It's incredible how just taking an image with a camera that you have in your backyard connects you to the thing that you study. In my case, I've been working on data for years, and I feel like working on that gamma ray data didn't connect me to space as much as in the sky as much as actually just taking a photo in my backyard of things. So now I'm just obsessed with it, and all I want to do is take pictures of stars, but I do have a day job, and today we'll be talking a little bit about that. Let's see, how do I advance? Cool. Since we're hot off the heels of Comic-Con, I felt like we might link some of this into popular culture a little bit, and talk about how gamma rays have kind of ingrained themselves into popular culture. And I have a few favorites that I'm going to go over. And the first would be obviously the classic Teenage Mutant Ninja Turtles movie, where some turtles in the sewers of New York, they come across some radioactive sludge, and that transforms these turtles into humanoids that can speak English, and then they're taught by their rat sensei how to do martial arts. And it's the mutations that occur in their DNA due to the radioactivity of the toxic sludge, which enables this. So when we're talking about gamma rays, we're not only talking about astrophysical gamma rays coming from outer space, but also just radioactivity in general. When we're talking about radioactive substances, we're talking about gamma radiation, and that links us to the astrophysics. So if you just hold on here for a little bit. For some, whoop, I don't want to skip this. Oh, does it just play? Let's try it. Okay. This is something near and dear to my heart. Star Trek, I think, got me through graduate school. I bought like all of the box sets, and late at night while I was working on my data, I was watching Star Trek. And something that's really interesting about the USS Enterprise are these are antimatter engines. And antimatter also, when antimatter, we'll talk about this in a few slides from now, but when a matter particle and antimatter particle collide and interact, they annihilate and they create energy in the form of gamma radiation and other photons. So that's how they power the USS Enterprise. This is probably the most classic example is the Hulk, where Bruce Banner came into contact with a gamma ray bomb that they were developing at the time, and he put his face in it, and then this mutated his DNA in a way to where now whenever he gets upset or angry about anything, he turns into a big green monster, which is pretty fun. That's the gamma ray bomb. Gamma rays are often depicted as green. I don't know why. Godzilla, obviously, is the king of the monsters. And this is a prehistoric reptilian that was awakened by radiation post-Hiroshima atomic detonations. So essentially a huge mutant lizard that can shoot plasma out of its mouth and perform all sorts of havoc on the city populations. There are all sorts of candidates. People get really creative about how they can integrate atomic physics and nuclear science into their superheroes. And it's really fascinating. You can tell that a lot of people put a lot of thought and effort into how they create these characters. And it's just been so fun for me to do a little bit of behind the scenes research about how some of the histories of some of these characters. This is just a small sample. And the origins of their superpowers and their and just the powers that they have in general. Interesting. I didn't know there was an animation here. Okay, I have an animation here. So when we talk about gamma ray astrophysics, I'm going to put this very loosely into 4 categories for today. Our compact object sources, we're going to call those the hulks of the universe. These are these extremely dense objects in the universe that defy our intuitions and our understanding of physics. Gamma ray bursts, these are the true monsters of the universe, and they come to us in these enormous bursts of energy, and they're extremely mysterious, but we're learning more and more about them every single day. And we'll talk about gamma ray bursts as well. Nucleosynthesis, so this is essentially probing the universe for the places and things where all of our atoms that make up our universe, make up you, make up our planetary systems, where they're originating. Nucleosynthesis describes how all of the atoms in our universe are being created and where they're being created and how. So that would be like probing the universe for the toxic sludge that's creating all of our turtles. And of course, antimatter. Antimatter, we actually have a probe into antimatter emissions in the form of gamma rays that actually looks like a really specific frequency or energy in gamma radiation. And essentially, we're probing our galaxy for where all of the USS Enterprise engines are occurring, where the antimatter is being created, and where that energy is coming from. So if we were able to probe the universe, we'd be able to see a whole bunch of these USS Enterprises flying around. So first we'll start about the Teenage Mutant Ninja Turtles of the universe. So our cosmic origins are very complex. The protons that are made up of your body came from the Big Bang. And through that process, they actually went through multiple stellar evolutions. And we're learning more and more about this as we're getting better at studying this stuff. The more we learn, the more extraordinary our origins become. And it's really fascinating to hear and to learn about the research that's going on that helps us understand our cosmic origins. We've all heard that we're all made up of star stuff, but it's actually really extraordinary the path that we got to get here. We're learning more and more that a lot of the elements, let's say, the calcium that makes up our bones, the iron that circulates in our blood, the carbon that makes up all life forms on Earth. These are all formed in the center of stars. And these stars are ancient ancestors that have now since deceased, and they've been reincarnated in us. And this is a really fascinating, amazing history that we like to follow. And gamma ray astrophysics helps us study this, our cosmic origins. Even more fascinating, in my opinion, is that a lot of the heavy elements that exist on this periodic table, you can see this periodic table is actually organized in our best hypothesis on where these elements are and how these elements are formed, whether that's in the Big Bang, all the hydrogen that we know of protons were originated from the Big Bang, but also white dwarf supernova, supermassive supernova. We know that as nuclear fusion starts fusing heavier and heavier elements, that efficiency drops off once we get to iron. So we know that we cannot form these elements in the furnaces of stars. And in fact, the vast majority of elements we think require a supernova to some degree. And a lot of the heavy elements, especially those that are essential to life, essential to our technology, gold, for example, we have strong evidence to believe that those came from a neutron-neutron star merger. Same with uranium. And this is really fascinating to think about how the prehistoric universe, how there's a mixing of spit between all these stars and stellar systems, and how these kind of mashed together into a cosmic stew that formed our current solar system. Do you have an answer to that?
If you're okay with it, we can send the slides around after.
Mm-hmm. Totally, yeah. I think that's fine. I'd be happy to like share this with all of you guys too. Or if you want to come see me, I'd be happy to share these slides with you personally too. This is my last slide on nuclear synthesis, but gamma rays actually give us a really unique probe into nuclear synthesis in that we can actually probe specific atomic radioactive isotopes that give us almost like a historical picture into the history of our universe. Different radioactive isotopes have different decay rates, and by probing different radioactive isotopes, you're essentially getting a history of all of the supernova that happened in history. And this gives us an example of this. This gives us an insight into the stellar evolution that happened in the past, not necessarily predicting what's going to happen in the future. It does help us predict what's happening in the future, but being able to probe these really specific radioactive nuclei. In our case, I work in MEV astrophysics or MEV gamma ray physics. There's a specific line that's iron 60, and the decay rate is around a million years. We have a few 100,000 years, and we have titanium 44, which is a probe that gives us about 60-year vision into the past. That tells us supernova that had happened in the very near future. So probing these radioactive isotopes in our galaxy tells us what happened in the past as far as stellar evolution. All right. We'll quickly move on to the antimatter origins in our universe and the USS Enterprises that are floating around out there. In my bandpass, in Mega EV or MEV bandpass, there's a really specific, very bright emission. It's the 511 keV emission, 511 kiloelectron volt emission. And this is the emission that occurs when we have the electron and its antiparticle, the positron. They interact and they annihilate and they create a very specific gamma ray at a very specific energy. That's that 511 keV. So by probing this 511 keV, almost like when you guys do your astrophotography in narrowband, you can cut out all the other nonsense and just probe that one very narrow emission that you see, whether it's H alpha, O through S3, or S2. 511 is our map to the antimatter that happens in our galaxy. And it's a very difficult signal to probe. It's actually a background signal for a lot of other payloads out there because it's so bright. It's kind of a mystery. I wouldn't say it's a significant mystery that our galaxy is very bright in antimatter. And the origins of this antimatter is even more mysterious. We would expect that maybe there'd be some sort of antimatter engine at the center of our galaxy around Sagittarius A star, where there's a lot of mass. We actually see a lot of antimatter emissions coming from the galactic plane too, and this is a mystery. We don't understand where these emissions could be originating from. So there are a bunch of telescopes out there that are probing this emission and trying to better understand where all of our antimatter engines are within our galaxy. And we'll talk a little bit more about that when we get to the specific payload that I work on in a few slides. All right, the hoax. I'm going to spend a little bit of additional time on the hoax because I think a lot of it will a little bit more directly relate to anybody here that does astronomy, visual astronomy, and astrophotography, because a lot of these hoax we can see in the visual spectrum. They have gamma ray counterparts, but they're also very, very bright in the visual spectrum, at least the ones that I'm going to try to showcase to you today. So this is a map that was produced by the Fermi Space Telescope. This is a high-energy gamma ray telescope. And what we're seeing is a map of all the gamma ray emissions coming from our galaxy. This image is in galactic coordinates, so the center of the galaxy would be right dead center. And as you kind of scan around, some of these objects you might be familiar with, right? I'm sure some of you have probably imaged the Crab Nebula. There's also Vela. The Cygnus region is right over here, and there's all sorts of high-energy emissions coming from the Cygnus region. And there's also some extragalactic sources, too, that are high above the plane. So we actually see a lot of emission coming from our galactic plane and galactic center. We also have gamma ray emissions that are coming a little bit from extragalactic sources, too. Okay, so the three compact sources I wanted to talk about would be black holes, active galactic nuclei, and neutron stars. So I'm very sure that most of you are familiar with stellar evolution, but I'm just going to give us just like a second to remind ourselves how black holes and neutron stars are formed. We start with our star-forming nebula. A bunch of gas starts to coalesce under its own gravity. We get our protostar, which is basically our planetary disks are formed. We get our main sequence stars. These can grow into supergiants in some cases if they have enough mass. If they have enough mass, they can also nova, supernova, hypernova, etc., depending on their mass. If it's a mass that is something around 20 solar masses, that's a candidate for a black hole candidate. If it's less than that, then it's often a neutron star candidate. If it's even less massive than that, then we could form things like dwarf stars, brown and white dwarf stars. Okay, so that's a really brief history there. Some of these black holes, and I'm very sure a lot of you also know about black holes, but essentially we get this fight throughout the star's life, where we have the pressure of the nuclear fusion that's pushing the star out, while we also have the gravitational pull of all the mass within that star that's pulling that star in. And towards the end of its life, as it's starting to fuse less and less efficient atoms into new atoms, the fight of gravity eventually wins, and then we get a supernova in the end, or nova. In our case, for a black hole, we call that a supernova. And what we think that is, at least from the mathematics, is that it's just a single point in space that has infinite density. It's a single point in space. You could shove an infinite amount of space into that point, or space into that point, and matter, and not space, an infinite amount of matter into that space. This is a phenomenon that a lot of our mathematics can predict, but the physics of it is kind of wonky. If you think about a point with infinite space, I think a lot of you are probably thinking that's probably not a physical thing, but we actually observe them and we see them, and they agree with all of our predictions to this point. So our physics there is actually really advanced, and we're learning more and more about them. And it's really annoying that these things exist because we don't really understand black hole physics to a high degree. But somewhere out there, there are these juggernauts of black holes that exist. This is an example of one, and I'm sure some of you have seen this image. This is the very first image that was released by the Event Horizon Telescope. The Event Horizon Telescope is essentially a collaboration of radio telescopes that try to maximize the angular resolution of these radio telescopes by collaborating with telescopes from all over the world, trying to maximize essentially the diameter of our telescope. And with the Event Horizon Telescope, they could get down to 20 micro arc seconds. 20 micro arc seconds is the resolution that they can achieve with the Event Horizon Telescope. If that doesn't blow your mind, I don't know what will, because that's insane. And the diameter of the dark halo of this is a black hole. It's Messier 87 star, and this is a black hole that's at the center of Messier object 87, which is a spherical galaxy. And this black hole has a mass that's equivalent to 6.6 billion suns. 6.6 billion suns in the mass of this black hole. It's a true juggernaut in outer space. If you were to place this black hole at the center of our solar system, the event horizon, which you're actually not seeing here, you're seeing more of the black hole shadow there. The Schwarzschild radius would actually extend past Pluto into the Kuiper belt multiple times over. It's humongous. Yeah, what else can I say about this object? The angular distribution of this is actually something like 50 micro arc seconds. So it's essentially like double that of the angular resolution of these telescopes. This might look familiar to some of you here too. This galaxy might be in your brain, and you're thinking this looks familiar. And there's a good reason for that. So a lot of you probably imaged the Markarian's chain, right? That's actually something that one of my first targets. My image is horrendous, so I didn't add it here. But this is actually gleaned from AstroBin. All the images I'm going to be showing are from AstroBin that I gleaned before today's talk. But this was taken by Dean Jacobs in 2023. This is from Anza Borrego in San Diego. So I did try to get images that were taken from here in San Diego. And M87 is actually this galaxy right there. One of the largest galaxies we've discovered. If you spend a little bit more time, that last image, I think you spent a few hours, but if you spend something like 26 hours and add some H alpha to it, you can actually get some of the H alpha that's actually interconnected between these galaxies. It's really pretty. And that's M87 up there. We're actually going to come back to M87 in just a minute. But in the meantime, there's another object that is up right now in Cygnus, which is the direct evidence of a planetary mass black hole. So this is the Tulip Nebula. I mostly know a lot of the common names for these objects because I'm new to astronomy. But right here is actually a planetary mass black hole called Cygnus X1. And that object is actually extremely bright in gamma ray emissions. It's very near to us. It's very, very bright. And in the optical, you can actually see the evidence from the jet that's creating these bow emissions right here in the O3. So you can actually see evidence of the jet and of this really high energy emissions, really high energy particles that are then colliding with the surrounding gas. You can point to it in an image that's a black hole, which is pretty cool. So if you haven't yet sought after this target, it might be something to go after this year. I've been like dying to actually get some clear skies so I can take a look at this thing. All right, the next thing that I wanted to talk about today are actually active galactic nuclei. And active galactic nuclei, they're closely paired to black holes, but what we're talking about are the center of galaxies where there's a supermassive black hole that's eating star stuff. It's not only eating star stuff, it's spitting it back out into the universe in the form of these relativistic jets that are very bright in radio, very bright in X-ray, and very bright in gamma rays, depending on the emission mechanisms. So this is actually an image that was taken by JWST. And we're going to talk about a few objects that we can view in the optical spectrum that we can actually image in your photos either this year or in the next couple of months. So this is AGN. This is a radio loud Seyfert 2 galaxy. This one's actually kind of difficult to image from San Diego. It's pretty low in the southern horizon. But if you, it is up and you can get it in the winter. But you can actually, if you add some H alpha subframes, you can actually see some evidence from the relativistic jet that's actually expanding on either side. This is something that I've always wanted to try to image myself. I've taken images with my, it was a balloon-borne gamma ray telescope that we've analyzed a bunch of data from, called the COSI Space Telescope, called the COSI Balloon-Borne Telescope. But I've never actually been able to image it in optical, and it'd be really fun to do that. Another popular target, this is another active galactic nuclei. This is M106. Has anybody here imaged M106 before? It's a really popular target. Cool. So this is an active galactic nuclei as well, but most of the emissions are actually coming from the bright core at the center. It doesn't have a relativistic jet or anything like that, but its core. If you've seen any really high resolutions of M106, it almost seems like a whirlpool that's going into the center of this galaxy. That's because we're getting all this mass flow into that black hole at the center of this galaxy. And now we're back at M87. This is really cool. I didn't actually know that you could do this until I started preparing these slides. But if you have enough reach and enough aperture, you can actually resolve the relativistic jet in optical. That's what you're seeing right here is actually evidence for the relativistic jet in the optical of M87. So if you have something like a 12-inch reflector with around 2,000 millimeters of focal length, this is something you might be able to image. And this is you imaging an active galactic nuclei spitting out star stuff, which I think is so cool. Okay, neutron stars. We went through our stellar evolution. Sometimes we get these really massive stars that collapse into black holes, but sometimes they're not quite massive enough to essentially collapse space-time itself. And what we end up getting is, as all these atoms come crashing down to the center of the star, they end up ejecting all the protons and electrons from the atomic nuclei, and what we end up getting is essentially solid neutrons. Solid, and we call this is actually the most massive form of matter that we know that exists in the universe, called neutronium. If you were to be able to scoop up a little bit of neutronium in about a pint of your beer, that would be equivalent to the entire mass of Mount St. Helens in the glass of your hand. So the stuff is extremely, extremely massive. And the cool thing about neutron stars is that they inherit the angular momentum of their star. So stars are almost always, every single star we've ever seen is rotating, has some angular momentum. And just like an ice skater who's doing a spin, her or his arms start out wide, and then when they bring them in, that angular momentum is conserved. This is brought to the extreme of a neutron star, where we have something that is the size of Betelgeuse collapses into something that has a diameter the size of San Diego. And this results in angular rotation rates of, in some cases, a few seconds per millisecond, a few rotations per millisecond. So these are rotating at these unbelievable rates, and as a result, they're producing these really, really high magnetic fields. And as a result of these really high magnetic fields, they're ejecting high energy particles into outer space. Some of these we can see in gamma rays, especially the ones where the magnetic poles are actually pointed at Earth. These types of neutron stars are called pulsars. They're called pulsars because we get grazed by the magnetic field and the jet of particles and photons that are then aimed directly at us. So what we see is as this thing flies through, as this thing is rotating in space. Yeah. This is a really popular target. This is actually a neutron star and it is a pulsar. It's the Crab Nebula. This was taken by Peter Morrison in San Diego. It's about 12 hours of exposure, but I think it's a really honest take at the crab. Sometimes I see images and I'm like, there's no way I'm ever going to get anything like that. But I think this is something that is a really good rendering of the Crab Nebula. It's in Taurus. I tried imaging it one time. I got like an hour of exposure, and it looked so bad. It was so noisy. So I didn't include it here. But it's a nearby pulsar that you guys can image in optical, and that's pretty amazing. I've even seen people do like time lapses of this nebula over time to do the time to see how it's expanding over time. That is really cool to be able to do an optical. If this is a target that you're revisiting every year or every few years. This is another very, very popular object. I do have an image of this one. I don't include my images because basically all of the things that I'm referencing here, I have like really bad images for them in optical. But this also contains a potential neutron star candidate. It's not confirmed, but kind of in this little nook of the Jellyfish Nebula, there is a neutron star nebula. The emissions appear to be like they come from a neutron star, but we haven't actually determined whether or not there's a neutron star there or not. And then we have S147, the Spaghetti Nebula, and this is another confirmed neutron star and pulsar that you can image. So this is actually one that I've never attempted to image. The neutron star is essentially like right dead center of this nebula, but this would be a really fun one to try to image, especially now that I got a Rokinon 135 millimeter lens. So this is a really wide target, and now I feel like I could finally try to actually image this target. All right, and then this is the last object that I wanted to talk about today. The last class of high energy objects that I wanted to talk about today. And these would be the gamma ray bursts, and these are the Godzillas of our universe. These are these time domain things that occur in sometimes fractions of a second, but sometimes they last several seconds or 2 minutes long. And in this fraction of a second, or sometimes multiple seconds, the entire energy output of the sun, it's billions of years of being a star, is emitted in the matter of a few seconds. If you think about all of the sunlight and all of the total power and energy output of the sun, imagine all of that being released in just a few seconds. That's what a gamma ray burst is. And we are so lucky that within our lifetime, we've seen a giant of a gamma ray burst. So gamma ray burst, it's 2210-109. Gamma ray burst 221009A. This happened in October of 2022. Is the brightest gamma ray burst we've ever detected in human history. Granted, like gamma ray astronomy is relatively new, but still, we're able to now detect these insane things that are happening out there in the universe. So this has been recorded as the brightest gamma ray burst of all time. That's where the boat comes from, the brightest of all time. Yep, the boat. Yeah, these are the most powerful class of explosions that we know of. We've never observed one occurring within the Milky Way itself. We have observed gamma ray bursts occur outside of our galaxy, of course. And we only expect maybe a few per galaxy per million years. So they're pretty rare. The origins of these events are still unknown, but we're actually learning a lot about gamma ray bursts in the recent years, and it's really exciting to learn more about them. We think they're we think it's likely that they're coming from neutron-neutron star mergers or black hole mergers, but there's still some uncertainty there in where they're coming from. This is an animation that shows all of the brightest gamma ray bursts that we've ever detected in human history. And we're going to get closer and closer to the boat here in the end. So you could really appreciate just how energetic this event was. So gamma ray burst 1901 14C, that happened in 2019. Gamma ray burst, this happened in 2013. Orders of magnitude brighter than the previous one. And now we get gamma ray burst 221009A. This is a monster in the universe. And it's saturated almost every gamma ray telescope in orbit. It was insane trying to process some of that data. We're getting to the point in high energy astrophysics where we're able to peer into astrophysical phenomenon from many different wavelengths. From gamma ray to X-ray to gravitational waves to optical, ultraviolet, etc. Observing the same thing using different wavelengths, and they all tell you a different story about that object and the physics that's underneath it. Probably the best example of this was the very first gamma ray gravitational wave event published by the LIGO Observatory, which is a gravitational wave observatory. And this is a perfect example of what it means to do to be doing multi-messenger astronomy. Multi-messenger astronomy is essentially observing the same physical phenomena through various wavelengths. So we think that this object was from a neutron-neutron star merger, and we first see the gravitational waves ripple through LIGO, and then we see I'm sorry, this got a little pixelated here, but we see a following emission in X-ray, gamma ray, ultraviolet, optical, radio. We saw it across the board, and at the exact time we expect to see them because they arrive at different times depending on how they're propagating through the universe. This is the gold standard of what it means to be able to do multi-messenger astronomy. When I was an undergrad, I was in an astrophysics class, and I remember us talking about LIGO, and it had been active, I think, for 10 years at that time. And my professor kind of joked about it, saying that it was never going to detect gravitational waves. And now we're seeing them all the time. We're doing astronomy with gravitational waves. We're actually doing gravitational wave astronomy now. And to me, that is an incredible thing. Um, um, so the gamma ray bursts that come several seconds later, but I actually can't read these for the other wavelengths. I'll show you on my computer maybe after we're done here. All right, so we've just gone over some of these mutants and monsters and how fascinating that they are. And I just wanted to maybe do just a really quick plug about just NASA space science in general. This is NASA's astrophysics fleet that it just published this year. And we have a bunch of our homies. We have the Hubble telescope, which is probably, I would say, the GOAT as far as its contributions to our science and our ability to reach the public to explain the science that we do. Hubble has done has had an immense impact on that. And Chandra is an X-ray telescope. XMM Newton's an X-ray telescope. Fermi, we saw Fermi's beautiful gamma ray images. NuSTAR is an X-ray telescope, a space telescope that has really, really amazing angular resolution, and so on. JWST, obviously, we launched probably the most ambitious mission that NASA's ever embarked on ever, and it was a success. And that's crazy that we were able to do that. We have all these other missions, Euclid, XPRISM, Sphere-X. Nancy Roman is actually going to be launching at the end of August. And Nancy Roman is another one. It's going to be another one of these cosmic reporters that is going to help us communicate how important it is to learn about the universe. It's similar to Hubble, but also it's as 100 times the field of view of Hubble. It's going to be incredible to see the first images out of the Nancy Roman Space Telescope. And this is mine, or not mine, but that's the one that I work on. It's COSI. So COSI is the Compton Spectrometer and Imager. That's an MEV gamma ray telescope. I started at UC San Diego as a postdoc working on a balloon-borne mission that was also COSI. We we design the telescopes, we do a proof of concept on a balloon platform, and then we eventually proposed to NASA to be a space mission. It's a small explorers mission, and NASA has all these different classes of missions. It's a small explorers mission. So we got selected for a phase A study, which means we were in competition with several other payloads at that time, other instruments at that time. So we got through phase A, B, C. Every single one of these phases was incredibly grueling, but we eventually got the news that we were selected, which is the highest ranking of a NASA mission. That essentially means we've gone through all the review, we've demonstrated all of our technology, and NASA just gives us the thumbs up to build it, which is amazing. It's such a privilege to be a part of this. Honestly, I can't believe that I get to do this. And we have all these other telescopes here, but Pueo I'll also give a shout out to. That's what I did my my graduate work on. It's an ultra high energy neutrino observatory that we fly in a big balloon and we detect radio Cherenkov emissions from the Antarctic ice sheet. We use the ice in Antarctica as our detector, and then we're looking for ultra high energy neutrino emissions from the Antarctic ice. And the predecessor of what I worked on is Pueo. And they're a fun mission. It's a really cool class of missions if you guys get a chance to check it out. One thing I do want everybody here, and I think I'm preaching to the choir here. Politics obviously ebb and flow, but right now our space science is under a really unique threat. Chandra, Fermi, Tess, Roman they were trying to cancel Roman. They canceled COSI in the presidential budget. Luckily, we have a Congress that kind of they're not totally insane, and they're like, we're not gonna cut the NASA budget by 65%, which is what the president's budget was, to cut NASA space science by 65%, which is devastating. Obviously devastating, not only to all of our scientists, but just the loss of standing that we have in the world. Not only were those canceled, essentially almost every single instrument that you see here, I can't think of any that weren't, their funding wasn't significantly reduced by something like 50%. We're just wiping this off the board in a way. So now is really the time to be advocates for our space sciences. So yeah, COSI is not canceled as of yet. The new presidential budget came around and they canceled it again. So it's like another year of hyper stress of this thing I've been working on for 10 years. Not just me. I came onto the mission later on. It's going to be canceled by an insane ebb and flow of politics and priorities that are going on right now. But as of today, COSI is actually due for launch in 2027. We're going to be out of Cape Canaveral on a SpaceX Falcon 9 rocket, which is actually very good for our science to get a very equatorial orbit. So we have essentially completely integrated our instrument, and we're actually it's integrated, and now we're calibrating, and we're actually getting ready by early next year to ship COSI to Kennedy Space Flight Center. Very, very busy time, but it's so exhilarating and exciting to be working on something so what I think is awesome. So I went a little over, I'm so sorry about that, but I want to do one more plug. So if you guys are interested in saving space science, here's a QR code that you could scan that takes you to the Space Science Advocacy Actions. That's on the AAS website. They have really amazing recommendations on ways that you can be active and trying to save our space science, which I really recommend you go and just creep on and see if there's anything that you feel interested in helping with. And lastly, I have a really quick plug for the Astrophotography Affinity Group at UC San Diego. I chair the Astrophotography Affinity Group and also the Outreach Group at UC San Diego. And our students are really desperate to have gear on campus that they can basically use to check out. And we were really grateful to have a few smart telescopes donated to our group. But what the students are asking, they told me to mention this. They would like a classic rig, a small refractor with a cooled astro camera. We also don't have a mount, so if anybody has any of those things, they could be ancient. It doesn't matter. They don't care. They don't have anything at this point. And maybe you go to this the garage sale or whatever you're calling it in a few weeks, and you can't sell something. if you want to donate it, we would really appreciate that. They also were asking for a solar telescope because we're in San Diego, and they've I don't think that they've really gone through the paces about like waiting for good weather, and they just want to maybe just try doing solar astronomy. So if anybody has a solar telescope, that's another thing that they asked me to ask you for. So thank you.